Welcome back. In this video, you will learn about the P-series. Let's get to it. Alright, so a P-series is another special type of series whose convergence we can easily determine. And so here is the general form of a P-series. We'll have the sum from n equals 1 to infinity of 1 divided by n to some power p. And that power p is usually a positive constant. And so here you can see what the first couple terms of a P-series would look like. You'll have 1 divided by 1 to the power of p, then the value of n will increase by 1, so then we'll have 1 divided by 2 to the power of p, and then the next term will be 1 divided by 3 to the power of p, and this would continue on forever. And so if we take a look at an example of a P-series, let's say that p is equal to 1, then we will have the sum from n equals 1 to infinity of 1 divided by n to the power of 1. Right? If p is equal to 1, then the power of n will be 1, and n to the first power is just n. So if I erase that power, then we have a P-series where p is equal to 1. Now if we write out the first couple terms of this series, it will look like this. We'll have 1 divided by 1 to the first power, plus 1 divided by 2 to the first power, plus 1 divided by 3 to the first power, and then we could continue on from there. We could have 1/4, then 1/5, 1/6, and so on. Alright, and notice that the first term is just 1 divided by 1, and that's equal to 1, so we can just rewrite that term to be 1. And so this is a P-series where p is equal to 1. In fact, this is a special type of P-series that we call the harmonic series. Alright, so you can make a note of this if you want. This is known as the harmonic series, and it is a P-series where p is equal to 1. Alright, so that's a basic introduction to what a P-series is, but the reason that it's important to be able to identify a P-series is because we can easily determine its convergence. And so here's the definition of the convergence of a P-series. If we have a series of the sum from n equals 1 to infinity of 1 divided by n to the power of p, it will converge if p is greater than 1, and it will diverge if p is less than or equal to 1. Alright, and so sometimes we call this the P-series test. If we have a P-series, we can test to see if it converges based on that value of p. If it's greater than 1, the series converges, but if it's less than or equal to 1, then it will diverge instead. Alright, and so these rules, we know they are true from the integral test. Right, if we were to perform the integral test on this general form of a P-series, we would see that these rules are true. And so let me show you what I mean. Here we have our general form of a P-series, and if we want to use the integral test for this series, we first need to take a look at the corresponding function to the series. And so that will look like this. We will have f of x is equal to 1 divided by x to the power of p. Right? We just take our series and we replace n with x and make it our function. And then what we do for the integral test for this function is test 3 different requirements, and if they are all met, then we can take the integral of our function from 1 to infinity and solve it to see if it converges or diverges, and that will tell us if our series converges or diverges as well. And so the 3 requirements that we need to check are, is our function positive, is it continuous, and is it decreasing? And this is all for the values of x from 1 to infinity, right? Those are the values of n that our series is defined for, and so those are the only values of x that we need to check for our function. All right, and so if we start with our first question, is this function positive? And just by looking at it, we see we have 1 divided by x to the power of p. For all of these values of x, if we plug them into this function, no matter what power p is, it's always going to output a positive result. Right? We're only working with positive values of x, and so it doesn't matter what the power p is. It could be 3, it could be 4, it could be 10, it doesn't matter. This output will always be positive. If we were also working with negative values, then that wouldn't be true. But since we're only working with positive values, this function will always be positive. And so we can say that the function is positive. Alright, and so next we want to check to see if our function is continuous. And so for our function, are there any values of x that would make this function undefined, that would cause a break in the function where it would not be continuous? And so our function is a rational function, and so the only way that this function will not be continuous at a value is if the denominator is 0, right? Because you can't divide a value by 0, and so it would be undefined. And so what values of x for this function would cause the denominator to be 0? Well, it's not going to matter what the power of p is. P is always going to be a positive constant, and so it's going to be greater than 0, which means that the only way that this denominator will be 0 is if x is equal to 0. And so, if you look at our interval here, we are not including the value of x equals 0. We are just looking from 1 to infinity, and so there's no values of x on our interval for which this function will not be continuous. The only value that would make it not continuous is 0, and that's not on our interval. And so we know that our function is continuous. And then finally, we want to check to see if it is decreasing. And the way we check that is to look at the first derivative of our function and see if it is negative for all values of x for our interval. And so, if we take the first derivative of our function, but first I'm just going to rewrite it a little bit. I'm going to say that our function is equal to x to the power of negative p, right? You can move that to the numerator by making the exponent negative, and now we can use the power rule for derivatives to find our first derivative. So f prime of x will be equal to our power multiplied down, and then we will subtract 1 from that power. So we will have negative p times x to the power of negative p minus 1. All right, now if we pull out a common factor of negative 1 out of negative p and negative 1, then our first derivative will be equal to negative p times x to the power of negative p plus 1. Right, we pulled out that negative from p and negative 1, so now we have negative positive p plus 1. And now, if we move x with a negative exponent to the denominator, then we will have that this is equal to negative p divided by x to the power of p plus 1. Right, that negative exponent now becomes positive. And so this right here is the derivative of our function, and as you can see, the numerator is always going to be negative, because remember, p is always going to be a positive constant, and so that positive constant will always be made negative, and the denominator here, we just have x to the power of p plus 1, that is never going to output a negative value since our values of x are all positive. And so, this negative sign is never going to change. Our derivative will be negative for all values of x on this interval. And so we can conclude that our function is decreasing. And so now that we have met these three requirements, what we can do is take the integral from 1 to infinity of our function 1 divided by x to the power of p times dx. And this improper integral right here is a special type of improper integral that we learned a rule for when we first looked at improper integrals. If you watched my video on improper integrals, you might remember that I called this a P-series, but I said we'd talk about it a little bit later. Well, now we're talking about it, and you can see that for this improper integral of a P-series, that we know it converges to 1 divided by p minus 1 if p is greater than 1, and we know that it diverges if p is less than or equal to 1. And so, remember, from the integral test, if the integral of our function here converges, then our series also converges. And so since this integral converges for p greater than 1, that is why a P-series converges if p is greater than 1. And in the same way, since this integral diverges when p is less than or equal to 1, that is why a P-series diverges if p is less than or equal to 1. Okay? And so that is why, when you have a P-series, all you have to do is look at the power of p, and if it's greater than 1, you know the series converges, and if it's less than or equal to 1, you know it diverges. Because of the integral test, we know that those rules are true, and they will work every time. And so that is where the P-series test comes from. Okay, and so now that you know what a P-series is, and how to determine its convergence, and where those rules of convergence come from, we can now look at some examples of determining the convergence of some P-series. Alright, so here's our first example. We actually already looked at this series earlier, but we didn't determine its convergence. This is the harmonic series where p is equal to 1, right? We have 1 divided by n to the first power, And so in this case, p is equal to 1. And remember that if p is less than or equal to 1, then we know that our series diverges. And so since p is equal to 1, the harmonic series diverges. And so that would be the final answer for the convergence of this series. Now for a second example, here we have the sum from n equals 1 to infinity of 1 divided by n squared. And so this is another p-series. We have 1 divided by n to a power of 2, and so that is our value of p. In this case, p is equal to 2, and 2 is greater than 1, and so since that is true, we know that this p-series converges, right? When the value of p is greater than 1, then the series will converge. And so we can conclude that this series converges. All right, let's look at another example. Okay, so here's our next series. We have the sum from n equals 1 to infinity of n to the negative third power. Now at first, this doesn't look like a p-series, right? We don't have 1 divided by n to some power p. But if we move n to the negative third power to the denominator, that power will become positive, and so we could rewrite this series to be the sum from n equals 1 to infinity of 1 divided by n to the third power, and now we can identify this as a p-series. In fact, we can see that we have 1 divided by n to the power of 3, and so 3 is our power p. So we'll say that p is equal to 3, and since that is greater than 1, we know that this p-series will converge. And so I'll write that down, that this series converges. Okay? So the value of p was greater than 1, and so we know for a fact that this p-series converges. Here we have another example. For this series, we have the sum from n equals 1 to infinity of n to the power of negative e. And so in the same way that we rewrote this series, we can rewrite this series by moving n to the negative e power to the denominator to make that power positive. And so this would be equal to the sum from n equals 1 to infinity of 1 divided by n to the power of e. All right, so now we can see that we have a p-series where we have 1 divided by n to the power of e, and so p, our power, is equal to e. All right, and so is e greater than or less than 1? Well, e is approximately equal to 2.7 and some more decimals, and so 2.7 is greater than 1, and so we would say that e is greater than 1, and since it is greater than 1, we know that this p-series will converge. And so we would say that it converges. Okay, let's take a look at some more examples. All right, so next up we have this series, the sum from n equals 1 to infinity of 1 divided by 3 times the square root of n. All right, now the first thing I notice here is that we do have 1 divided by n raised to a power, but it's not initially obvious what that power is because it's expressed as a square root. But remember that a square root is the same as taking the value to the 1/2 power, and so we could rewrite this to be the sum from n equals 1 to infinity of 1 divided by 3 times n to the 1/2 power. All right, and so now you can see how this is in the form of a p-series. Now it's important to note here that we do have a constant multiple of 3 in the denominator, or you could view it as a constant multiple of 1/3 to the whole fraction, but don't let that trip you up. A constant multiple for a p-series is not going to affect its convergence, right? In fact, we could pull out that 1/3. This would be equal to the sum from n equals 1 to infinity of 1/3 times 1 divided by n to the 1/2 power, right? If we were to multiply these two fractions back together, we would have this expression right here. And then we're always allowed to pull out a constant to the outside of a sum, right? 1/3 does not involve n in any way, and so it doesn't need to be within the sum. We can just pull it to the outside, and so this would be equal to 1/3 times the sum from n equals 1 to infinity of 1 divided by n to the 1/2 power. And so now you can see that that constant multiple of 1/3 will not affect the convergence of this p-series. We still have 1 divided by n to the power of 1/2. All right, and so the power p is equal to 1/2, and 1/2 is less than 1. It's not greater than 1, it's less than 1, and so in this case, this p-series will diverge instead. And so we say that it diverges. All right, so a couple important things to take away from this example is that a constant multiple does not affect the convergence of a p-series, and if that value of p is less than 1, your series will diverge. Okay, and one more thing, just be careful, we're only talking about constant multiples here, not affecting the convergence of a series. If you were to instead have another term in the denominator, let's say we had plus 1, this series would no longer be a p-series. All right, so do not say that this is a p-series and then it diverges based on the power of n. We will look at how to determine the convergence of a series like this that is similar to a p-series in a later lesson where we will actually compare this series to a p-series. All right, but for now, don't worry about that. What you do need to know is that a constant multiple does not affect the convergence of a p-series. All right, here's another example. We have the sum from n equals 1 to infinity of 4 divided by the cubed root of n to the 5th power. All right, so similar to our last example, don't let this 4 trip you up. It's just a constant multiple of 4, and so we don't really need to pay attention to that 4. It's not going to affect the convergence of this p-series. And if we look at the denominator here, we don't explicitly have n raised to some power. We might need to rewrite this a little bit in order to truly see what the value of p is for this p-series. And so remember that taking the cubed root of a value is the same as taking that value to the 1/3 power. And so in this case, we could rewrite our series to be the sum from n equals 1 to infinity of 4 divided by n to the 5th power to the 1/3 power. Right, we're taking the cubed root of n to the 5th, and so n to the 5th to the 1/3 power is the same as that. Now, if we simplify this expression, we can multiply the exponents, right? We can have 5 times 1/3, and that will be the power of n. And so we could rewrite this to be the sum from n equals 1 to infinity of 4 divided by n to the 5/3 power. Okay, so when you have n raised to a power, and that is raised to a power, you can multiply those powers to have 1 power of n. All right, and so now we have a p-series where we can see that the value of p is equal to 5/3. And 5/3 is greater than 1, right? 3/3 is equal to 1, and so 5/3 must be greater than 1. All right, and so since the value of p is greater than 1, we know that this p-series converges. Okay, let's take a look at a different example. All right, so here's our next example. We have an infinite sum of terms that we can express as a series. And so what we want to do is determine what that series looks like and then determine if it converges or diverges. And so what we want to do is develop an nth term. And so to do that, we need to look closely at each of these terms. And so if we label each of our terms, we have a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. And after a sub 1, we can see a pattern with the rest of our terms, right? We have 1 divided by the 5th root of 2, then 1 divided by the 5th root of 3, then 1 divided by the 5th root of 4, and 1 divided by the 5th root of 5. And so based on the value of n for each term, it's safe to assume that the first term would be 1 divided by the 5th root of 1, which of course is just 1, and so you have 1 divided by 1, which is 1. And so it looks like the pattern here is that each term is equal to 1 divided by the 5th root of n, right? For a sub 2, n is equal to 2, and we have 1 divided by the 5th root of 2. For a sub 3, n is equal to 3, and we have the 5th root of 3, and this continues on for the rest of our terms. And so this is the nth term of our series, and so we can express this series as the sum from n equals 1 to infinity of 1 divided by the 5th root of n. And remember that the 5th root would be the same as taking n to the power of 1/5, and so this is equal to the sum from n equals 1 to infinity of 1 divided by n to the 1/5 power. And so now you can see that we have a p-series that represents this infinite sum of terms where p is equal to 1/5 and 1/5 is less than 1. All right, and so since our value of p is less than 1, then we can conclude that this series diverges. Okay, so we were able to find the p-series that represents this sum of terms, and because of the value of p, we can say that that series diverges. Let's look at one more example of a p-series for this video. All right, so here's our last example. We have another infinite sum of terms that we want to rewrite as a series and then determine if it converges or diverges. And so just like we did with the last example, we want to determine what a sub n is, the nth term, and we have been given a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. And so comparing those values of n to each of the terms, we can clearly see that there is a pattern going on here. When n equals 2, we have 1 divided by 2 times the square root of 2. When n equals 3, we have 1 divided by 3 times the square root of 3. When n equals 4, we have 1 divided by 4 times the square root of 4. And when n equals 5, we have 1 divided by 5 times the square root of 5. And so I believe it's safe to say that a sub n is equal to 1 divided by n times the square root of n. Whatever that value of n is, we multiply that value in the denominator by the square root of that value. And that would still hold true for a sub 1, because 1 divided by 1 times the square root of 1 would be 1 divided by 1, which is just 1. Okay? And so our series will be the sum from n equals 1 to infinity of 1 divided by n times the square root of n. Now this doesn't quite look like a p-series in its current state, but we can manipulate it a little bit and then you will see that it is a p-series. And so remember that the square root of n is the same as n to the 1/2 power, so this is equal to the sum from n equals 1 to infinity of 1 divided by n times n to the 1/2 power. And now we can multiply these two values together and add their exponents, right? When you have x squared times x to the 3rd power, that's equal to x to the 5th power because you add the exponents. And so n to the 1st power times n to the 1/2 power will be equal to n to the power of 1 plus 1/2. And 1 plus 1/2 is 3/2, and so this is equal to the sum from n equals 1 to infinity of 1 divided by n to the 3/2 power. Okay, so we just added 1 and 1/2 to get 3/2. And so now we have a p-series where the value of p is 3/2. So if p is equal to 3/2, and that is greater than 1, right, because 2/2 is equal to 1, 2 divided by 2 is 1, and so we can say that since that value of p is greater than 1, that our series converges. All right, and so that is it for this example. We were able to express this infinite sum of terms as a p-series that we could then determine the convergence of based on the value of p. All right, and so with that is all I had for this lesson on p-series. If you want to see some more examples of p-series and determining their convergence, feel free to check out my examples video that I'll have linked at the end of this video as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.